Let's start with looking at carbon-13 NMR. It's kind of the simplest one that we can think about. We're going to get one peak per unique carbon, right? So we're looking at carbon nuclei, their spin, which are going to be really, really sensitive to their surroundings. Again, like every other spectroscopy experiment, this is non-destructive. It's going to require something between 10 and 100 milligrams. So it's not particularly the most sensitive analysis we can run. But sometimes if we have only a little bit, we can just essentially take the data over a longer period of time to get around that problem. So for instance, this is 1, 2, 3, 4, 5, 6. This is hexane. How many C13 peaks would we expect for a hexane? Well, remember, there's a line down the middle here, right? So these carbons are the same, these carbons are the same, these carbons are the same. And so we're only going to see 3 peaks for hexane because there are 3 unique carbons. How about here, 2-methylpentane? We can kind of see now our symmetry is a little bit different. There's only one of these, so 1, 2, 3, 4. These methyls are rotating fast enough on the NMR timescale where we would call those methyls the same. So they would show up together and we would see 5 peaks. Also, we really can't even, the height of the peak doesn't really tell us how many how many carbons we have. Sometimes peaks are shorter, not because there's fewer of them, but because of sort of chemistry reasons that we'll get into. How about this one though? So this one, there is no symmetry in there. Every carbon is different. You might say, aren't these carbons kind of the same? They're all CH2s, kind of away from everything else. Yes, they are very similar, but C13 is very, very, very sensitive. And so we actually would expect to see slightly different frequencies for these carbons over here. So if this is 1, 2, 3, 4, 5, 6, 7, 8, I would expect fully 8 NMR peaks for that carbon, or for that molecule. What do these numbers mean? These numbers are frequencies. They're essentially talk about the photon emitted when we flip spin states. And we express them in parts per million. What that essentially means is we're taking the frequency of the nucleus that we're looking at, and we're subtracting a frequency of a particular compound, TMS, tetramethylsilane. And we're dividing by that standard frequency. So what's special about this compound? Well, nothing really. What's kind of special about it is that silicon is kind of an electron donating group. It's pretty electropositive. And so this is considered a very shielded compound in terms of the carbons and the protons, right? So we can think of this as being a particularly electron-rich compound. So what does an NMR printout looks like? It looks like this. So essentially we've got peaks around an x-axis. The peaks that are to the right, smaller numbers of this ppm, are considered shielded. So they are feeling less of that big external magnetic field. And they're shielded because there is electron-rich nuclei. So there's lots of electrons around them, shielding them from that magnet. In the old school nomenclature, we sometimes call this upfield because it requires an upfield magnet to flip them. It's kind of confusing for people because here upfield means lower numbers in ppm. But the big thing is that this is shielded. This end of the spectra is electron-rich compounds. The other end, just the opposite of all this stuff, we would call these nuclei de-shielded. So maybe there's some electron withdrawing group around it that's pulling electrons away from it. And so that nucleus is electron poor, right? Nothing shielding it from that big magnet. And sometimes we also call this downfield. Okay, let's talk chemical shifts. So these are the frequencies that we'll see carbons show up in a carbon-13 NMR. Really, really briefly, we're just going to think about 4 buckets to put these peaks in. The first bucket, from 0 to 50 ppm, are alkyl, sp3 carbons. The second bucket, from 50 to 100, is sp3 bound to oxygen. Oxygen's very electron withdrawing, and so it's going to de-shield peaks, bring them farther to the left. We're not going to talk about nitrogen or chlorine or anything else. If it's less de-shielding than oxygen, it'll probably be in the middle here somewhere. Usually our most common solvent is CdCl3. The C in deuterated chloroform is going to show up around 77, and it's going to be a triplet. Why is that? Well, it's a long story, but the deuterium makes it into a triplet instead of a singlet, and I'll explain why later. So again, sp3 carbon 0 to 50. If it's de-shielded by an oxygen, we're thinking 50 to 100. From 100 to 150 is going to be sp2 carbons, so carbons with double bonds generally to other carbons. The most common we'll see is aromatic carbons. Benzene itself shows up around 128, so aromatic carbon shows up around that range. Above 150, we're going to see sp2 carbon bound to oxygen. That's usually going to be ketones and ketones, aldehydes, esters, acids, etc. Ketones are on the far end of this, 200 and above. Esters and acids are a little bit lower. But remember that this also counts for phenols, right? So this carbon here is an sp2 carbon bound to oxygen. And it's pretty de-shielded. It shows up right around this 150 line. Phenol itself shows up at 155. But again, all of those are sp2 carbon bound to oxygen. So these four big buckets is kind of all I know and all you really need to know about C13 NMR. Are there peaks that don't fit in here? Yes, again, we're not talking about nitrogen or sulfur or anything. I'm not even talking about alkynes, which are usually somewhere in here. But this is generally good enough to help you solve your problem. Here's BHT. It is a very common food preservative. If you have a cereal box next to you, if you look on the bottom, it probably says you have some BHT in there, butylated hydroxytoluene. Excellent antioxidant for reasons that we'll cover next term in Organic 2, but it has to do with how stable that radical would be. So here we go. Test yourself. How many different C13 peaks would I expect for BHT? So we can count 7 different unique carbons for BHT. There's a line of symmetry down the middle. And so we've got 1, 2, 3, 4 unique ring carbons. This one is just that one is just that one. This methyl is obviously unique. We've got 2 of these that are the same, so only one counts. And then because we can rotate around that tert-butyl group quickly, all 6 of those methyl groups are identical, so we should see 1 peak. But now let's assign their chemical shifts, right? So here we said that this is in that 150 to 100, or 150 to 200 box. So this should be sp2 bound to oxygen. There's only one sp2 carbon bound to oxygen. It's this one, so that's A there. Then we can see we've got 3 different carbons in that sp2 carbon box, so just double bonded carbon, and those are going to be these 3 here. For today, we won't sort of worry about which one is which, but they're all kind of in that box. E, we've got 34, 30, and 21, so those are all going to be the sp3 carbons not bound to oxygen, so here, here, and this quaternary carbon. Here's what the C13 spectra for BHT looks like. So you can look at these peaks and you can see that although some are bigger than others, there's not a good quantitative relationship between how tall the peak is and how many carbons are under it. Right? So for instance, these peaks should be exactly the same height, those peaks should be the same height, these peaks should be exactly twice as big as those. This peak should be 3 times as big as that, not 2, etc. So the quantitative relationships for heights don't hold for C13. They will hold for proton NMR, which is going to be the next thing that we talk about. But this is what your typical C13 spectra looks like. Our big thing is counting the peaks to see how many unique carbons we have, and then to kind of box them in that 0 to 50, 50 to 100, as I said before. And also, remember that when you see like little peaks around 77, that is usually the solvent that you're going to do. That's CdCl3, which is you can safely ignore. It's not going to be the thing you care about.